Hi everyone, my name is Yahav Bechavod. I'm a PhD student at the University. This video is about joint work with Christopher Jung and Stephen Wu. This is somewhat of a generalization. However, on a high level, the majority of the work that we have seen in algorithmic fairness pertains to statistical fairness guarantees. Some consider a rich collection of possibly overlapping subgroups. However, even these notions are limited in the guarantees they can offer to individuals. Here's an illustration taken from Kearns et al. Let's assume for the sake of the example that we wish to equalize acceptance rates. We can see that the criterion holds for groups defined by a single feature. However, as we move to a final level, by considering intersections of features, things break completely. This was only a simple illustration, and we note that even group fairness definitions that are defined over a rich collection of possibly overlapping subgroups may still break when considering the individual level. A different notion of fairness that was introduced by Dwork et al. Aims to provide guarantees on the individual level in the form of a Lipschitz-like condition on the predictor, which is inspired by the assertion that similar individuals should be treated similarly. A crucial part of the definition hinges on the availability of a similarity metric between individuals in the context of a specific task. This metric, however, is often unavailable. It is also often unclear how such a metric can be acquired in the context of many tasks. Our approach suggests a solution to this problem by employing a human fairness auditor, an expert in the relevant field, providing the algorithm with fairness feedback. What type of feedback? Well, we can try and ask the auditor for the exact formula that measures fairness in his mind, but this may be very difficult for him to answer. Another suggestion is to ask for the exact distance between any two individuals, but this is still a bit hard to specify, especially for a large number of queries. Finally, what we suggest instead is querying the auditor for fairness violations. Can you spot a pair of individuals who are similar but were treated very differently by the algorithm? This is inspired by the idea that while the exact formula of fairness may be hard to specify, the auditor instinctively knows unfairness when he sees it. Our setting is the online contextual learning setting, where on each day the learner deploys a policy, then k individuals arrive and are predicted using the deployed predictor. Finally, the learner has two types of feedback: the true labels of the individuals and fairness feedback from the auditor, indicating whether or not the deployed predictor induces a fairness violation on some pair of the individuals who arrive. And this process repeats itself between days. Our results are the following. As we've seen, the problem that we are trying to solve is online fair batch classification. So first, we introduce a regret-preserving reduction from the fair online learning setting with additional auditor feedback to the standard online learning setting by constructing the fake stream of examples. The upshot is that given any algorithm for standard online learning, we can translate its regret guarantees to upper bound both the accuracy regret, but also the number of fairness violations in the original set. This holds true for any adversarial arrival of individuals. A second result is if we had the assumption that individuals are drawn from a distribution, that we are able to prove generalization guarantees for both accuracy and fairness for the average policy over the run of the algorithm. Here is a short comparison with prior work. Note that our results do not require the similarity function to actually be a metric. This could be important in practice, as feedback from the human auditor may actually not have any metric form. The type of queries to the auditor are regarding violations rather than numerical distance queries, and the auditor in our formulation is only required to report a single fairness violation rather than all violations, which could be difficult in practice. To summarize, our approach removes the classical metric assumption. Auditing is made easier, where the auditor only needs to report a single fairness violation if any exists. Finally, our results come with no parametric assumptions on the hypothesis class or on the similarity function. and our algorithms can be implemented using Oracle efficient online algorithms. In the adversarial arrival setting, we guarantee no regret for both accuracy and fairness. And in the stochastic arrival setting, we can additionally prove generalization for both accuracy and fairness for the average policy. The full paper is on arXiv. Thank you for watching.